Welcome to this second appointment about model-based design with MathWorks suite. Today, as Professor said, we will go through the steps that we show you last time, but in this time, we will show you how to implement these steps in a real case scenario. In particular, we want to analyze a case study that is the motorbike that I showed you last time. Is a model based on Arduino, so a very prototype stadium model that will help us to show and to try our code on an effective hardware. Of course, we will go deeper with the components when we deploy the code. So for the moment, what we want to point out is the system that we have and our goal for today. So we have our motorcycle model with the actuators and the sensors that I will explain in a moment. The Arduino, that is the core board able to be programmed by Simulink from Simulink, and so is the link between Simulink and the hardware, sensor, and actuators. And finally, as I said, MATLAB and Simulink. All of these want to be the tools to create a self-balancing motorcycle. So we want a motorcycle that is able to keep it straight in the vertical position without the help, of course, of any external forces. There are three subpoints that we can develop under this main topic. The first is the most simple one, of course, the steady self-balancing. So what I mean is a simple balancing on the place. The second one is the balancing in straight motion. So we can activate the rear motor, the drive motor, and see if it is able to be balanced also during a straight motion. And finally, the last and most challenging task, that is the balancing while steering, of course, because more complexity entering the system under analysis. I want to start from the end to make you understand what is effectively our goal. Here you can see our motorbike. The first task is this one, so the steady self-balancing. As you can see, the inertia wheel is rotating in one direction, and the motorbike is balancing on itself. Very important notice, of course, without the movement of inertia wheel, the motorbike will fall off. Same thing for the second task, so directly linear self-balancing, as you can see. And finally, the third task, so the curved self-balancing. So now we have a full overview of the three tasks that we want to achieve. Let's take, if you remember, the same 4 points that we developed last time all together in order to go through the same development now with the real motorbike in mind, so with a concrete objective. Let's start from the plant modeling. So our system is a motorbike. So in the case of perfect vertical aligned, we are in an equilibrium position. In fact, we have that the center of gravity is placed anywhere in the center of the motorbike. Let's suppose at the point of contact, the center of rotation of our motorbike is on the contact between the tires and the terrain, and we can create this vector, this distance between these 2 points, that in case this vertically aligned, our gravity force is acting in parallel to this vector r, and as consequence, we are in a perfect equilibrium. In fact, we know that the torque produced by some force, in this case the weight P, is the cross product with the vector linking the center of rotation and the point of action of the force. In this case, the two vectors are parallel. As consequence, the torque produced is zero, and effectively our motorbike in this special case will be perfectly balanced. Of course, this is an ideal case because you know that, first of all, more probably the center of gravity is not maybe perfect centered, as in our real case, because our motorbike is not perfect. But in general, all of the noise or all of the disturbance that the environment and the real model have is subject to, of course, make the motorbike more on this stage. Of course, this is exaggerated, but we can suppose that we have a lean angle that rotate the motorbike on one of the two sides. In this case, of course, means that now the weight have a momentum, can apply a torque on the center of rotation, and as in consequence, our torque is not anymore zero. We are in an unstable equilibrium. So, as you can probably imagine, if you have ever driven a motorbike or a bicycle, it is not self-balancing as in a normal situation. Now, so this is the problem that we want to tackle. We have an unstable equilibrium. We want to stabilize this equilibrium. And the actuator that we want to use is the so-called inertia wheel. I told you sometimes now these terms. Inertia wheel is a simple cylinder, the gray cylinder that you can see, that have some weight and consequently some inertia that we can exploit in order to apply a torque on our system, an external torque. So we know that the torque produced by the torque of the inertia wheel will be equal to its inertia. So its inertia multiplied by its acceleration. Now, of course, since we know that for every action there is an equal and opposite reaction, we know also that the torque, if we compute the equilibrium between the motor and the inertia wheel, we can understand that the torque of the motor will be minus the torque of the inertia wheel in order to be balanced, the two. But the motor is connected to the bike, so we can transfer the torque produced directly on the bike. So maybe now you have a more clear idea on how we can act on the system in order to produce a torque that counterbalance the torque produced by the weight and in a stable equilibrium. So let's take again our motorbike. Now we have the real model. These two pieces are meant only to avoid the motorbike to fall off completely and maybe damage. So there are no part of the motorbike system actually. But as before, we can write the equation that of equilibrium of the entire motorbike. Now we have that the inertia of the motorbike multiplied by its rotational acceleration will be in equilibrium with the torque produced by the gravity and the torque produced by the inertia wheel. So, as I said, we can develop these two torque. The first one is equal to the weight multiplied by with the cross product with the connection between the center of gravity and the center of mass, that is in this case developed as the sinus of the angle theta, and the torque of the inertia wheel that, as I said, is minus the torque of the motor. The torque of the motor is the variable that we can use to act on our system. Okay. Of course, will be not the torque, but the current, because we will drive the motor in current, but it is the input of our system. Now, fundamental that we can write all the equation all together. So substituting the terms tau g and tau iv in the global equation. And doing this, we can obtain the final equation that we will use to make our system in equilibrium. Okay, so this is the equation that describes our system with as input the torque of the motor, as output theta. Very important, as you can see behind, that theta is measured from the vertical alignment. So when theta will be 0, will be our objective, because theta 0 means that the motorbike is vertical aligned. Okay, now the second step. As I said last time, the second step is the controller synthesis. So now we have our system. We want to create a controller. We want to design a controller able to stabilize our system. So let's start from the equation that I showed you one moment ago. The equation, the canonical equation that I showed you a moment ago, could be rewritten with the Laplace form. So substituting the double derivative with s squared. Doing this, we can also, defining tau as the input variable, tau motor, and theta as the output variable, we can define, as usual, the transfer function that link the torque of the motor with the position with respect to the vertical alignment. So we have our plant that is described by this transfer function, and we have our controller. Our controller that we decide to use is a PD. We will show you both a simple proportional controller and a proportional and derivative one, only for to show you what are the difference between the two. Of course, we are using a negative feedback action in order to stabilize our system. Of course, we tune our Kp and Kd in order to make the system stable. All of these steps are done offline. Before starting coding in Simulink, you can tune your controller in order to make the system stable. So we have our G, okay, is the same as before with the number substituted into the variable. We decide to use this controller. So with K proportional 1 multiplied by 10 at -2, and 5 multiplied by 10 minus 3 for the derivative part. We can obtain the open loop transfer function multiplied by G. And since we have a positive pole, a pole with a real part that is positive, the 6, 1, we should require that our Nyquist diagram for the Nyquist criterion will go around the -1 point with 1 circle in the counterclockwise direction. Okay, so we can prove the stability of our system in this way, and so we are ready to implement. Now, so we have our plant completely modeled. We design our controller in order to make the system in equilibrium. We are ready to go straight on the simulation and the integration part, because remember, we want to make the process of the model-based design complete. So now that we have our controller, we want to test it before on the simulation. Testing on the simulation, as we told you last time, make it possible to prevent some possible issues and damage the real motorbike. So let's start with this third step. So first thing, in order to obtain the simulator for our system is to create the model in Simscape. Now, for our model, we have different components. We have, first of all, the front wheel, the back wheel, the two cylinders that we can use to represent these two main components. We'll have the steer column that is actually actuated. We will show you in a moment in order to perform also the curved trajectories. The body, the main body of the vehicle, and finally the inertia wheel that is our actuator on the system. Now, here there is the SimScheme block scheme. I reported it here. Not it is simply a screenshot, but I want you to go all of this step in a detailed way. So if you remember, as I said last time, one thing that is common to all Simscape scheme is this free standard base component. So the word frame that I can remember you, it is the first link in order to connect the model to the word system. The configuration panel, where you can set, for example, the gravitational forces and so on, and finally the solver that is fundamental to make your simulation correct in order to have the right output from the simulation. Next, we have this little block is simply a transformation, a rotational transformation of the coordinates, but it is fundamental, this joint, that is the joint able to describe the movement of our motorbike. In fact, you can think that we modeled our motorbike as a vehicle, a motorbike, with the contact between the wheels and the ground. So normally a vehicle, it is described as the two wheels in contact, of course, with the ground. In our case, of course, this is true, but it is not required for our analysis. We want, in fact, to analyze the movement around the equilibrium position, so we can model our motorbike, in this case, with a simplified Simscape simulator that describe only the movement around this axis. So we are actually creating an inverse pendulum with an hinge in the back between the ground and the other part of the vehicle in order to study this dynamic of the vehicle. As I said last time, there is not the perfect simulator, but there is the correct simulator for each case. In our case, we are not simulating the dynamic of the vehicle, so we don't require any other more complexity to be modeled. So we have this hinge that you can see have an external torque. This external torque will be used simply to impress some noise on the equilibrium, because as I showed you one moment ago, ideally our motorbike without any noise, without any disturbance, will go perfectly balanced in vertical. We want to make a little bit more similar to the reality. Same thing for this sensor, these two sensors, theta and theta dot, that measure the position and the derivative of the position, so the speed of rotation respect of this joint, so the rotational speed. Now we have the real wheel that is directly connected to this joint. So there is the ground, the joint, and the real wheel. The real wheel is connected to the body, to the steer column, and to the front wheel. Fundamental importance is taken by the actuator of our system, that is represented by this bottom right part. In fact, we have another joint, another rotational joint, because remember that our inertial wheel is actually rotating with respect to the body of the bike. And so this other joint will be actually actuated by the motor torque, as we can see. And we will sense the speed of the motor in such a way to control actually the speed, because we will need, of course, to impress an acceleration and so control the speed. Finally, we have the body of the inertia wheel, so the mass and the cylinder of our inertia wheel. Fundamental to note these blocks, small arrows, one white and one black. These are the blocks that give you the possibility to convert a signal that is in Simulink environment, for example, external torque or motor torque, to a signal that is in Simscape variable. So it is required in order to make the two systems working in parallel, but with the differentiation needed to simulate these two environments. Okay, this is the first input. This is the first output for the noise of our motor. Now, all of this block is our simulator. Our simulator that now we can integrate to the control scheme that we show you a moment ago. So we have the simulator that provide already theta and theta dot. And for this reason, we can use directly the theta dot provided by the simulator to integrate the KD, sorry, the derivative part of our controller, that is this block, is done directly on the derivative of theta, because it is directly sensed by our system. Here, these two blocks are instead the external noise that I showed you a moment ago, where we want to, with a white noise that is this block, generate an external torque in order to make the vehicle fall on one side. So now that we have the Simulink test, now that we have the complete control scheme, so the model and the controller, we want to perform our test. We show you how and why we should use this test, but in general, you need to place your goal in some point, so maybe some performance goal, and verify that your system in simulation is actually able to follow these requirements. So in our case, we decide that the two different controller that we could use, so the proportional controller on the proportional plus derivative, should make the motorbike be make the motorbike in equilibrium around the vertical position with an angle of 0.5. So if we go behind or more than 0.5 degree, we will have the fall of the motorbike, the fault of our system. So you can see here how we set up, and we will show you in a moment the real Simulink, but this is the controller, so we can select the motor torque or with the proportional controller or the PD controller. And in order to implement the test, we can simply take our theta, we make the modulus of theta, we check through the comparison with 0.5, and through this block assertion, we can check if the assertion is true or false and compare it with the result. The result is that in fact, if we use the proportional controller in this graph that show you in the red, the red line is showing you the theta value. So it is going from 0 to 1 in this case. You can see that the other plotting, that is the assertion, so the red dot, are green if the assertion is verified, red if it is not. And so we can see that when the theta goes beyond 0.5, that is this position, the assertion will fail. And so after our simulation, we can check that actually with only a proportional controller, we are not able to satisfy our requirements. So we should go a little bit deeper. In fact, if we change the controller using a PD, the other one that I show you in the design of the controller, we can see that the same assertion, starting from 0 degree, will go through it will go converging to a asymptotic value, in this case 0.45, but the controller now is completely satisfied always. In fact, you can see that the green dot are always present. But what this mean from the point of view, from the qualitative point of view of the motorbike behavior? We will show you in a moment in the Simulink, but I can anticipate that, as you can see from the video, I hope that you can see, with only the proportional controller, the motorbike is not perfectly stable. In fact, there is an oscillation on the position, whereas with the proportional plus derivative controller, we can balance the motorbike more in a more stable way. Now I give the word to my colleague Alberto that will show you first of all the simulator, the simulator where we take these two videos, and next the implementation part of this motorbike. Thank you.
Exactly, thanks Daniele. Some seconds. Just to Professor to switch the sharing of the screen. Thanks. Perfect.
Should be done now.
Yes. Okay, very good. Here we are with the. Okay. Here we are with the let's say Simulink test. Okay. We have, as Daniel explained, the model of the motorcycle and the controller. In this case, we have a test that is slightly changed with the one that we just showed you, because we want to let's say point out that we can also build complex assertion. In this case, we have a switch here that enable the control action. So it's a more, let's say, visual, intense representation of the test, because as you understand from the video, it's very small, the test that we use for the let's say slides. So we decided to modify it a little bit to better improve the let's say the visual impact of this test. So we have put here the assertion block, and we are ready to run this test for around 20 seconds. Here the signal is composed by 0, so we have no control action for a certain time, for second. Then goes to 1, so we enable the controller, and we will see that the controller stabilizes the system even if it is oscillating, and then we switch back the controller to off, and so we will see that again the system will return unstable. Okay, we can play run. Some seconds for the compiling of the system. Good. The simulation is ended, but we have here the video. So for some seconds does not work the controller, then it starts working, it stabilizes the system. You can see here the wheel is spinning, and then once it's in a vertical position, it stays still because we don't have any further let's say interaction. So at the beginning the controller was off, so the motor falls. Okay. Here the controller goes off. Sorry, I was confused. So for a little bit the controller goes off and the motor starts fall down. Then when the controller goes back on, it returns in the correct position. So as we can see here, we have a set of the simulator. We have a visual representation, but at the end we can also do the let's say the plotting of the data. So we can see the theta, okay, and for the beginning of the test until the switch off the controller, we have 0. Then when we switch off the controller, it starts spinning. So of course we have a behavior that physically is not possible, but it's quite, let's say, clear for the visual point of view that the motor starts falling down. And then when we switch back the controller, it returns to the 0 position. And we can also have the assertion, okay? So we said for this little period, the motorbike fall down and then goes back on because we activate again the controller. Okay, let's say that this is a little explanation about how the assertion works. Of course, when you have to deal with this type of criteria, you usually have a set of assertion that is quite complex and let's say also very related with the model. We here have only put 2 type of assertion, but of course you can have many of them and much more strict. Okay, so let's go back to the presentation and let's see about the what's going on. What are the last point, the integration. Okay, speaking about the integration, we have the complete motorcycle. The complete motorcycle, as we already see a little bit on the demo part, is composed by different components, but the main one is for sure the inertial wheel. Inertial wheel that is connected to the motor, okay? But in order to control this motor, we need also to provide the power through a battery, okay? And all this flow of power is managed by the control board that is in charge of let's say convert the straight up power from the battery into some voltages and consequently current for the motor. Okay, so let's see also the other components on this motorbike, because there are many of them. First of all, the Arduino Maker 1000, that is the core of the system, and it is the brain on which will run all the code. Attached to it, there's the motor carrier board, that is a hardware specifically built and designed in order to handle power from the battery to the motor. So you have here some connector and some hardware part that is enabled to deal with high power. High power that doesn't mean hundreds of watts, but something that can burn the let's say the electronics of a control board such as the one of Arduino. On top of these 2 boards, there's the IMU shield that I will explain later the functioning, but it's something that is in charge of acquiring information about the angle of the motorbike. We have also the rear motor with the encoder, so the motor in charge of the motion of the system in a straight line. So at the beginning of the presentation, Daniele showed you that we have the possibility to move in a straight way the motorcycle, and it's done by the rear motor. Then, as I said, there's the inertial wheel, and in the front there's the servo motor in charge of the control of the steering angle. So we can select the correct orientation of the steering by means of this motor. And last, we have the ultrasonic sensor that for now is not used, but has the possibility to acquire distance if we want to build a more complex control algorithm for this motorcycle. And then the LiPo battery. But let's stress out a little bit what is Arduino. Arduino is the core of the today implementation, because it's a low cost, so very few euros of components, very used in the maker world because it's very very supported. So MATLAB, as I explained yesterday, has lots of already built components, blocks, in order to interface with this type of electronics. So for the beginners, using Arduino in this type of project allows a straight implementation from Simulink to the control board. And then last, has the possibility to acquire data from the different pins of this board, both in a digital way or in an analog way. So you can acquire continuous quantities, such as a value of a sensor, or you can also have the possibility to acquire data from any digital device, such as the one that can communicate with zeros and one. Okay, perfect. We have now two different approaches to model the Arduino. Of course, since now we have spoken about the Simulink implementation, but with the board comes also the Arduino IDE. So a line control, let's say control environment, in which you have to write down the code in order to be able to run the Arduino. Of course, we have some advantages on Simulink, because we can have the possibility to use all the blocks that already we know on the block library, and usually is more easy to program because you need less programming skills, but more conceptual, let's say, ideas. In the other hand, if you want to use the Arduino IDE, you need to know, of course, the programming language, but probably you will have a little bit more efficient code. Okay. Of course, there's always pros and cons. You have to define your trade-off to best suit your application. Okay. Speaking about the special Arduino that we have put on our motorbike, we have the so-called Maker 1000. And it's a special Arduino because not only provide the connection with DC and analog pins, so digital and analog pin out, but also has a Wi-Fi module. Wi-Fi module that is very helpful in our case because we can detach the cable that we use to program the Arduino, and we can run a standalone code on the device without any let's say restriction due to the physical means to connect it to it. Okay. Of course, let's say the specification of this board are not let's say the powerest on the market. If you compare it to your, let's say, standard laptop or PC, it's very low power. But you have to understand that here you are loading a code that is very optimized and very efficient in order to handle this type of problem. You don't have to run any exotic system or so on. So you can handle this type of control action also with this type of low power board. We said also that on Arduino we connect the so-called motor carrier that is in charge to control both the traction motor and the inertia wheel by means of a specific hardware that can switch the phases of the motor in order to create a specific tension, and so the required current to generate the set point of the torque. Okay, so it's a, let's say, not a straight understanding, but of course it's the way in which we control the motors. Also on this board we can connect the servo motor, the front servo motor, the power in from the battery, the switch, so the one that allows to switch on all the system, and the Hall sensor that is in charge to understand the speed of the inertia wheel, as I will explain later. Okay. First of all, let's start from the rear motor. The rear motor, that is the one in charge of providing the motion, the linear motion of the motorcycle, is composed by the magnet and the encoder that together provide information about the angle of the motor. So to precisely control a motor, you need to know exactly in which position is in order to, let's say, do some type of position control or velocity control. And in this case, there's an hardware in charge of this type of acquiring this information, that is the encoder. Attached to it, there's the DC motor, that of course is the one that provides the motion, and a gearbox. The gearbox is in charge to, let's say, reduce the speed and increase the torque. So to, let's say, to have a more powerful torque with less speed, because of course this is a very small motor, so has a small torque, and we need to increase it to drive the motorcycle. Okay, and of course there's the output shaft. Perfect. At the end you have this block in Simulink, that is the motor, DC motor control, that is exactly the let's say the software implementation of the motor. In Simulink, we will see you don't have to think about how to manage this type of components, but you have only to put some information inside the blocks and then Arduino, and then when you proceed to the compilation of the Simulink will include all the libraries and the information to be able to control this type of systems. Okay. Speaking about the inertial wheel, as I just said, we have a way to understand how fast it's spinning. In this case, we don't have an encoder because it's not required. We have an Hall sensor, a sensor that can understand the spinning of the wheel by counting the number of passes of the magnets in front of this sensor. So with this sensor, we understand how fast the wheel is spinning, because each time a magnet inside the inertial wheel is moving in front of this sensor, we have a spike. So we count the number of spikes and we know exactly how fast the wheel is spinning. Okay. Then, speaking about the IMU, that is the main, let's say, component to provide feedback to the whole system. So is the component in charge of acquiring the information about the position of the motorcycle. So we can acquire the accelerometer and the gyroscope. So when we have the motor in a vertical position, we will have only, let's say, in the accelerometer part, okay, on the left part, we will have only the gravity force on the system and 0 on the two other axes, okay? And on the gyroscope, we will have 0, 0, 0 because the motor is steady still. It's stopped, okay? When we start the experiment and the motor start falling in one side or in the other one, then the gyroscope will provide an information about the angles and also the derivatives, so the speed of the falling. And with this information, we will be able to control the system. So it's the sensor in charge of acquiring the information about the position of the system. Okay. Then the two of them, so the IMU and the Arduino are connected through a bus that is very is a smart way to connect components, because allows to first of all interchange information in a easy way, but second of all you can attach different let's say devices. If you have one Arduino that is your and you need to acquire different sensors, you don't have to connect each one of them directly through a dedicated connection, but you can use a bus and using the I2C buses. Okay, perfect. Last component that I will describe is the battery. The battery that is the one that provides, of course, the power to all the system, and it's characterized by the voltage and the capacity, and the two combined generate the power. And so also we can understand that there's another factor that is the peak current, so the capacity multiplied by discharge rating, that, let's say, are not the focus of this presentation, but it is important to understand that all these things are going to be involved in the control of the overall system. Of course, also here we have the specific block for the implementation in Simulink. In this case, is battery read, that will provide the information about the voltage of the battery. Okay. Now that we have described all the parts, let's see how they are implemented in the overall system. So the one that is in charge of the control of the motor. In particular, we have, first of all, the control of the inertial wheel, that is our main actuator. The inertial wheel will receive an input from the controller, that is the torque command, that will be scaled by a scaling factor and will be provided to the motor. Then the IMU, so the Hall effect sensor that is connected to pin 16 will provide an information about the speed of the inertial wheel, that through a rate adjuster will be adapted to the speed of the execution of the controller and will be output to the overall system. Then, second, we have the rear wheel. In this case, we have, again, the control of the rear wheel, so the input from the controller. If we want to say, okay, motor, go straight on or stop, okay, then there's the output of the system, that is the rear wheel speed, and the connection between the two is the block that I described earlier, that is the motor connected with the encoder. In particular, if we want to control the motor, we have to put, again, a scaling factor to properly scale the control action. And then to read the encoder, we have this, that is the discrete derivation of the steps, because, again, the encoder will set a series of steps. If I take the derivation, we know exactly the speed of the motor. So from a counter of the steps to a speed, a revolution on the speed. Okay. Moving on, we have the information about the battery. So we have the information about the voltage of the battery that need to be casting into a double. So it provides an information that is a type of data that is an int 16 that must be casted to double, then must be converted through a scaling factor, and then we end up with the battery voltage. Okay. Then we have the IMU. So with the block Arduino IMU, we can acquire the information, and then these information are split into three things. First of all, the Euler angles, so the theta, and theta angle. So we have the three angles on the IMU. So if you take your axis, you have the three angles, and in this case we want only to know the angle of the motorcycle, so the theta angle. And then also it appears the rate of changing of this angle, so we know the theta, and the theta again of the angles. So we have theta dot. Now that we have both the information, we can also take information about the the calibration of this sensor, because again, being a real sensor, it needs to be calibrated in order to be sure that it acquires the correct angles and it doesn't I don't know, doesn't be affected by any corruption of the information. Okay. So when we have all these signal provided by the IMU, we are quite ready for the implementation of the overall system, because we have also this little part that is the bias. Why we add this part? That is one of the things that last time I was speaking about. I mean, last time I speak about the fact that when we want to implement something, we deal with the so-called operating modes. Here we have something that must be considered also. So when we switch on the system, it can have a little bit of bias respect to the zero angle due to, I don't know, specific nonlinearity of the sensor, or the weight that is not perfectly distributed on the system, and so on. So we need to add a little bias corrector that in this case is in charge of adjust the theta non-idealities. Okay. Okay. And then now we have all the parts involved on this type of controller. But what is missing? It's missing something, because again, here would be the exact straight implementation of the controller we have developed, but it's missing the specific safety function in order to be sure that this model will not hurt or damage itself. Okay, so in particular we have we need to check the speed of the inertial wheel. We have to check the IMU correctness. So again, earlier I said that you can acquire the information, but if you acquire the information and you don't do any type of test of this information, it's useless to acquire that information. Okay. Then again, check the battery voltage. If the voltage is too low, you cannot drive the motor properly. So maybe you encounter some problem on your controller because you think about your control action or any possible bad behavior. But if your battery is low and you don't check the correctness of the voltage, maybe you end up with some strange behavior. And then the last, but for sure one of the most important, is the fallen status. So if our motorcycle start falling and touch the ground, you need to stop all the simulation in order to avoid that it start, I don't know, spinning or doing some strange behavior. Okay. For example, let's treat about how we can make this model more robust. Okay, we have to implement the safety function that I just explained, and they are the one in charge of avoiding the dangerous situation. And for example, I would like to point out the one in charge of controlling the speed of the inertial wheel, because it's something that maybe can go out of the normal understanding, because let's say when we want to control this motor, we said we want to apply torque on the system, and to apply torque we need to, through our controller, apply an acceleration clockwise or counterclockwise. So we want to move and accelerate our inertial wheel in one direction or in the other one. But of course, accelerating one time, accelerating a second time, and so on, we can end up with a value of speed, so omega of this wheel, that is outside the nominal behavior. So outside this nominal behavior means that it can be very dangerous, because it's no longer something that is, let's say, it's outside the design of the actuator. Okay, so we need to put some type of saturation. Okay, first saturation that we can put is about the torque of the motor. Okay, so we said you don't have to accelerate too much because you are outside the nominal ranges of the actuator. For example, you know that in order to obtain torque from a motor, you need to provide current. If you provide current too many times, let's say in a very, let's say, easy way, this motor will heat up. So if you heat up too much, the motor will not work properly. But of course, this is not enough because, again, if you continue acceleration very slowly, you can end up again with a velocity that is outside the ranges. So we need also to provide some type of control on the speed of the inertial wheel. Okay, and this is, I don't know how to be very objective on this, but the point is that if you think only on the control action of your system, you never will end up thinking that if you do not put any constraints on the overall speed of the inertial wheel, you will have some problem. Because usually we think about the saturation of the control action because it's the only quantity that is very important and effective on our system. But when you have to deal with some complex and real system, you have to think at the overall scheme in order to be sure that none of the things you are controlling will produce some dangerous situation. So back to the speed of the inertial wheel, we said we want to be to put some constraint duration that in this case is 6,000 RPM on the inertial wheel, and then we have this block here that will the one with the control of the 6,000 RPM will control the speed, and then if it's not satisfied, it will provide a Boolean value, a 1, that will stop the simulation. So from something that is a continuous variable, inertial wheel speed, will provide some information that is Boolean that can be treated as an error. Okay. So we want to avoid outside the ranges. Now we have all the, let's say we have understood the type of control that we need to implement in our system to be sure that it works properly. And we need to see what's inside the core of this system. The core is composed by some black quantities. That means the information that will flow into the core of the system and the information that will flow out of the core of the system, and in red the error status. And also this type of color is important because allow the user to immediately understand what is the purpose of each one of these signals. And it's something that you cannot do very easily on the, let's say, programming standard IDE, such as the one I explained earlier. Okay, perfect. And in order to understand better all the precautions implemented, let's move to the Simulink. Okay. So, speaking about the Simulink, we have here something that is no longer black and red. I don't know why it's changed color in this case, but we have here a series of inputs and some type of controller. Okay, first of all, here is something you already seen. I just explained it. It's the control on the inertia wheel. Then here we have an example of the control of the IMU calibrated. So it provides an information. The information is checked with the current status, and if it's changed, it will say, okay, the IMU is no longer calibrated or need to be calibrated. Then a second point here is to check the voltage of the battery. So here we have battery read. If the voltage is above 10.5 sorry, if the voltage is above 10.5 volt, provide a 1 and combine it with the current status. If it change, we'll say battery voltage not good. Okay, all these control action are mixed together with one end, and then it goes to the so-called fallen status. So it means no longer if one of these conditions is no longer satisfied, it will go in a fallen status. Fallen status, that means stop the simulation because something is broken. Okay, it's very drastic. Maybe you can implement some more smart way, but in this case, we want to see something that is very, let's say, strict on this type of constraint. So if something does not work properly, you need to stop the simulation. Okay. Now that we are already on the system, I'd like to show you how to implement it into the real hardware. So how to perform the deploy phase. Okay. Okay. To implement it, first of all, we said we need to connect to the hardware. In this case, I would like to do a little change on my setup. Give me 1 second. I'm trying to.
Alberto, there is also a question about the magnet of the Hall sensor.
Yes.
I can answer.
Okay.
The magnet, as Alberto said, are required in order to measure the rotation of the inertial wheel. So we have two magnets in the inertial wheel. We have the Hall sensor that sense through the magnetic field of the magnet when the magnet pass in front of the sensor. So we, since we have this wheel that is rotating, each time that a magnet go behind, in front, sorry, of the sensor, we register a pass, a presence, and so we can understand the speed of the wheel through the computation of the time between one sensed and the other one. I hope that now it is clear.
Okay. Okay. Okay, I go on, and then if we have any other question, feel free to ask. Sorry, I didn't ask you if you have any question. Again, feel free to ask. Okay, now that you should see from my webcam the motorcycle. Okay, so we can see both the Simulink and the motorcycle. We have here connected the Arduino through this cable, okay, here. So they connected to the computer. We have, okay, with the switch here, switch on the system. Okay, so we are ready. The Arduino is connected and we are ready. On the PC, what we can do first, we need to go to the preference, and in hardware implementation, select the Arduino, okay, Arduino maker, and we are ready. Second, we need to specify some information because we want to connect it through. We want to connect it through the through Wi-Fi. Okay, so we go to Wi-Fi properties. We put the Wi-Fi ID and the password. And then we select which type of interface we want to use. So the communication interface is the Wi-Fi. Perfect. Okay. Then, as already explained, all these part of the Simulink, we are ready to click run. Okay. It will start the compiling. We can see the diagnostic here. take some time because it needs to build the code of the system. So it will take the information, develop the C code ready to be run on the Arduino, and then we will see that here we are providing a so-called run in external mode. I would like to repeat myself as yesterday. Running external means we will run the code on the Arduino, but we will need to be connected through the Simulink in order to acquire information and see the behavior of the last. In particular, here we have the information about the code that is generated, how big it is, and how full is the overall memory. And it says, okay, building complete. Perfect. Building complete, and here we can see that the code is running. Okay. First of all, I'm gonna detach the connection. With one hand, it's a little bit hard. Okay. And as we can see here from the interface, we are continuing to be connected. First of all, in order to run the system, here we need to be to calibrate the IMU. So we will take the motorcycle, do some, let's say, operation. Okay, like this. Okay, and then spinning the other way. Okay, one. Perfect. We have calibrated the system. Second, we need to switch on the torque command. So from 0 to 1, okay, already done it. Perfect. So we have connected the controller to the output. Why it's important to have this type of controller? Because if you want to do some type of test and you don't want that your wheel start spinning, if you don't are ready, you can put to 0. In this case, we are ready, so we put to connection. And then now, I hope you can see, if I put it on a vertical, it does not start spinning. Why don't know? Give me a second. It does not start. Okay. Not good. Okay. Does not start. We have a little problem. Let's try to
Alberto, try the back wheel. Maybe there is a connection problem, so we can see if the back the traction wheel is working.
Okay, we have a little problem. Maybe we have a problem, connection problem. Let's try again. Meanwhile, if you have any question, Daniele can answer it in order to avoid wasting time. Okay.
Yeah, these problems are quite normal with when you try to use a real hardware. The main difference between the Simulink programming, the standard programming, and simulation is, of course, that the hardware is exponentially more complex and lots of things could influence the test. That's like in this case that maybe there is a problem with the USB cable or maybe the Wi-Fi. Could depend. If you have a question, guys, ask. Feel free to ask. Okay, I can add only something in the meanwhile. Now Alberto is actually using a mode that is called external mode. We described you this modality last time, but let's remember that this mode is designed for this type of test, because you have not the final release of your software, so you are still testing your software, and maybe you need to have a clear feedback from the sensor and the variables inside your system. So using this modality, the external mode, you are actually running the code on your Arduino, as actually Arduino would be completely separated from Simulink, but keeping a link between Simulink and Arduino. We can see through the serial communication the quantities and the signals inside the system. Now, the point is that in this case, the system is a little bit more complex, because in order to have the motorbike to be used freely without the cable attached, as Alberto said, we use an external mode with the Wi-Fi enabled. So we use the cable in order to deploy the software and connect to the motorbike. Once we have connected to the motorbike and deployed the software, we are sending to the Arduino also the information about the SSD and the password of a Wi-Fi net, in order to be able, once we have deployed the software, to detach the cable and use the motorbike without any obstruction. Okay. Alberto,
exactly.
you're ready?
Thanks, Daniele. Now we are ready. I only recompiled the code. Probably there was some missing dependency or something that was not perfectly built. We are now ready because, first of all, the motor here at the front wheel puts itself to 0. So we are providing the information of the correct angle. So if we try to steer it, does not work. Second, we are ready to see the functioning of the inertia wheel. So if we try to put it in a vertical position, okay. Here we are. For some second, it stays in a vertical position. Okay. It is not exactly the best performance. We can try to fix it through the use of the bias here. So we can say, okay, a little bit less of out of centering, let's say, coefficient.
I can add that the point here is the one that I described you before. Normally, ideally the motorbike, if would be perfectly aligned, all of the components, the weight distributed perfectly on the left and the right, we would have 0 degree as the equilibrium point. That's not the case, because, of course, as you can see, this is a prototype we built with our hands, and so the battery, the other components could influence this performance. In fact, in the video that I show you at the start of this lesson, the performance were real, the motorbike were the same. Actually, we try to put the battery in the best position possible, to set up the equilibrium point as best we can, and finally the result was that one. Of course, online is a little bit more difficult to fine-tune these special things.
Exactly as Daniele was saying. Of course, there's many options to improve this type of software. We are not here to say this is the best solution possible, and we are far from the best solution possible. But with this example, we want to show you that it's possible to do it. And of course, we don't have to be worried or scared by the use of hardware, but with the correct, let's say, steps that we explain, you can be able to program any type of board or the, let's say, configuration you want, okay?
And if I can add, the two issues that we encounter, so the connection one and maybe the performance that are not the optimal, but we can improve them, of course, are not a single case, but when you work with hardware, I don't know your experience, but when you work, when you go from the poor programming in a simulation environment to an implementation, these problems are very frequent, of course. You need to be able to face this problem because actually they are no problem, but they are the everyday life for the implementation part. You need to take into account plenty of difference between the ideal simulation world and the hardware world that is not, of course, ideal at all. So
okay.
Okay.
I think that we can go back to the presentation and see if there's any question. We are here to answer. Or
I can add that this engineering kit is actually sold on the website. You can find online, but there is no it is not necessary to buy such a complex kit. There is very small, lots of different examples, different smaller steps you can buy from wherever you want some kit and start programming Arduino with both its IDE with Simulink and try this thing that we show you. Okay.
Good. So thank you, Daniele and Alberto.